there is something hiding in the space between stars, something we cannot see, cannot touch, cannot measure with any instrument we have ever built. It makes up most of our universe, and yet we have no idea what it is. Right now, as you lie in bed, you are surrounded by mysteries so profound that they shake the very foundation of everything we think we know about reality. Think about that for a moment. Every scientist, every telescope, every billion-dollar experiment is trying to answer questions that our ancestors asked while sitting around fires thousands of years ago. What is this place we call home? Why does anything exist at all? And the strangest part is that the more we learn, the less we seem to understand. The ancient Babylonians looked up at the night sky and wondered. The Greeks built philosophies around these questions. The Egyptians encoded their cosmic curiosity into pyramids that still stand today. And here we are, with all our technology, all our knowledge, all our sophisticated equations, and we are still asking the same questions, still staring up at the same stars, still completely mystified by the universe we live in. But here is what makes it even more fascinating. In the last 100 years, we have discovered that 95% of everything that exists is completely invisible to us. We have found that particles can be in two places at once. We have realized that time itself might be an illusion. We have detected signals from deep space that repeat with such precision that they seem almost artificial, and then they vanish, never to return. Tonight, we are going to explore 100 facts about the mysteries that keep scientists awake at night. Not the things we know, but the things we do not know, the gaps in our understanding, the questions without answers, the phenomena that defy explanation. Some of these mysteries live in the darkest corners of space, where galaxies spin in ways that should not be possible. Some hide in the smallest particles of matter, where reality itself becomes fuzzy and uncertain. Some exist in your own mind, in that strange inner experience you call consciousness, which no one can quite explain. We will talk about stars that disappear without a trace, about objects flying through our solar system that accelerate in ways that break the rules, about experiments that seem to show particles communicating faster than light, which should be impossible, about the hard problem of why you experience anything at all, why there is something it is like to be you. Hey guys, tonight we begin with the remarkable mysteries that have puzzled humanity since the dawn of time. The unexplained phenomena that keep scientists awake at night and philosophers pondering for centuries. From dark matter to consciousness itself, from vanishing stars to signals from deep space. Their story is one of wonder, curiosity, and the beautiful acceptance that some things remain beyond our grasp. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now dim the lights, maybe turn on a fan for that soft background hum. Get into your blanket and let's ease into tonight's journey together. Because the universe is not what it seems. And the first mystery we need to talk about is the one that changed everything. The discovery that most of what exists is made of something we have never seen, something that might not even be matter as we understand it, something dark. Imagine you are looking at a spiral galaxy through a powerful telescope, beautiful arms of stars swirling around a bright center, rotating through space like a cosmic pinwheel. Now, here is the problem. When astronomers calculated how fast those outer stars should be moving based on the visible mass of the galaxy, something was very wrong. The stars on the outer edges were moving way too fast, so fast that they should have been flung out into space like water droplets flying off a spinning wheel. The gravity from all the visible stars, all the gas clouds, all the dust, everything we could see was not nearly enough to hold the galaxy together. And yet there it was, perfectly intact, spinning peacefully through the void. This was not just one galaxy. It was every galaxy. Everywhere astronomers looked, they found the same impossible thing. Galaxies were behaving as if they had 5 times more mass than we could see, as if something invisible was holding them together. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying galaxy clusters when he noticed something strange. The galaxies were moving so fast relative to each other that the whole cluster should have torn itself apart billions of years ago. He calculated that there must be some kind of dark matter providing the extra gravity to keep everything bound together. People thought he was wrong. They thought his calculations had errors, but he was right. Decades later, astronomer Vera Rubin confirmed it beyond any doubt. She spent years measuring the rotation speeds of galaxies and found the same pattern everywhere. The outer regions of galaxies were moving at the same speed as the inner regions, which made no sense at all. It was like watching a merry-go-round where the horses on the outside edge move at the same speed as the horses near the center. That is not how rotation works unless there is invisible mass spread throughout the whole structure. So scientists concluded that dark matter must exist. It has to be there because without it, the universe as we see it cannot exist. Galaxies would fly apart. Galaxy clusters would dissolve. The cosmic web of structure we observe would never have formed after the Big Bang. Dark matter makes up about 27% of the universe. It is everywhere, even passing through your body right now, and we have absolutely no idea what it is. Is it made of particles? If so, they are particles unlike anything in the standard model of physics. Scientists have built detectors deep underground, shielded from cosmic rays, waiting to catch a single interaction between dark matter and ordinary matter. They have run these experiments for years, and they have found nothing. Whatever dark matter is, it barely interacts with normal matter at all, except through gravity. Some theories say dark matter is made of weakly interacting massive particles called WIMPs. Others propose axions, tiny particles that would be produced in huge numbers. There are ideas about sterile neutrinos, primordial black holes, even modifications to gravity itself that would eliminate the need for dark matter entirely. But so far, after decades of searching, we have not detected a single dark matter particle. And then there is something even stranger: dark energy. In the late 1990s, two teams of astronomers were studying distant supernovae, trying to measure how fast the universe was expanding. They expected to find that the expansion was slowing down over time because gravity should be pulling everything back together. Instead, they found the opposite. The expansion of the universe is speeding up, accelerating, getting faster and faster. This discovery won the Nobel Prize because it was so shocking. Something is pushing the universe apart. Some kind of energy that fills all of space, acting like anti-gravity, driving galaxies away from each other at an ever-increasing rate. Scientists called it dark energy, and it makes up about 68% of the universe. Think about that. Dark matter is 27%. Dark energy is 68%. That adds up to 95%. All the stars, planets, gas clouds, black holes, everything made of atoms, everything we can see and touch and measure, all of that is only 5% of what exists. We are living in a universe where we only understand a tiny fraction of what is actually there. The rest is dark, hidden, unknown. Nobody knows what dark energy is. The leading theory is that it is a property of space itself, a vacuum energy that exists everywhere. But when physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get an answer that is off by a factor of 10 to the power of 120. That is not a small error. That is the worst prediction in the history of science. Some scientists think dark energy might be changing over time. Others wonder if it is connected to extra dimensions we cannot perceive. There are models involving scalar fields, quintessence, phantom energy, but the truth is, we are completely in the dark about dark energy. And there is more. Our galaxy, the Milky Way, along with thousands of other galaxies, is being pulled towards something, a massive gravitational anomaly known as the Great Attractor. It lies beyond the zone of avoidance, a region of sky obscured by the dust and gas of our own galaxy, so we cannot see what is pulling us. We just know that we are moving toward it at over 600 kilometers per second. Beyond that, there is an even larger structure called the Shapley supercluster, and beyond that, something is creating what astronomers call dark flow. Entire galaxy clusters moving together in a particular direction, as if being pulled by something outside the observable universe, something beyond the cosmic horizon that we can never see. Then there are the cold spots. When scientists mapped the cosmic microwave background, the afterglow of the Big Bang, they found spots that are colder than they should be. One particularly large cold spot cannot be explained by current models. Some think it might be evidence of a collision with another universe. Others say it could be a massive void, a region where very little matter exists, but nobody is certain. Every answer we find seems to lead to deeper questions. The universe is not just mysterious, it is made of mystery. In 2015, astronomers noticed something that should not exist. A star in the constellation Cygnus, officially cataloged as KIC 8462852, but nicknamed Tabby's star after the astronomer who discovered its strangeness, was dimming in a way that made no sense whatsoever. Stars dim all the time when planets pass in front of them, but those dips in brightness are regular, predictable, and small. Usually a planet blocks about 1% of a star's light. Tabby's star was dimming by up to 22%, and it was doing so in irregular patterns that defied every explanation scientists could think of. Some dips lasted days, others lasted weeks. The pattern was chaotic, and none was coursed. At first, researchers wondered if it might be a swarm of comets, but that would require an absurdly large number of comets, all happening to pass in front of the star at once. They checked if it could be dust clouds or debris from a planetary collision. For a brief moment, people speculated about something more extraordinary. Could it be an alien megastructure, a Dyson swarm of solar collectors built by an advanced civilization? The idea seemed wild, But when you eliminate the impossible, whatever remains, however improbable, must be considered. Scientists pointed radio telescopes at the star, listening for signals. They found nothing artificial. The mystery remains unsolved to this day. Then there are the fast radio bursts. In 2007, astronomers discovered brief pulses of radio waves coming from deep space. These bursts last only a few milliseconds, but release as much energy as the sun produces in an entire day. At first, scientists thought they might be glitches in the equipment, but more bursts kept appearing. Hundreds have been detected now. Most happen once and never repeat, but a few sources send out bursts over and over again in patterns that almost seem organized. One repeating burst, FRB 121102, sends signals that follow a strange cycle. For a while it goes quiet, then suddenly it becomes active for a period of time, then quiet again. The precision of this pattern is puzzling. Natural phenomena do not usually operate with such regularity. What could produce such powerful bursts? Theories range from neutron stars with incredibly strong magnetic fields to colliding black holes to something involving dark matter. Some scientists even entertain the possibility that these could be signals from extraterrestrial technology, energy beams from alien spacecraft traveling between stars, but we simply do not know. Speaking of signals, in 1977, a radio telescope in Ohio picked up something so unusual that the astronomer on duty wrote "Wow" on the printout. The signal lasted 72 seconds, was incredibly strong, and came from the direction of the constellation Sagittarius. It matched exactly what scientists would expect from an intelligent extraterrestrial source. They immediately tried to find it again. They pointed telescopes back at the same spot in the sky dozens of times over the following weeks, months, and years. The signal never returned. No one has ever heard it again. Attempts to explain it as a natural phenomenon have not been convincing. Some think it might have been a one-time event, like a collision between objects in space. Others believe it could have been a brief transmission that was not meant to repeat. The WOW signal remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. In 2017, astronomers spotted an object tumbling through our solar system unlike anything they had ever seen. It came from interstellar space, passed close to the sun, and was heading back out into the void. They named it Oumuamua, Hawaiian for scout or messenger. At first they thought it was a comet, but it did not have a tail. Then they thought it was an asteroid, but its shape was bizarre. Observations suggested it was extremely elongated, like a cigar or perhaps a flat disk, about 400 meters long. But here is the really strange part. As it swung around the sun and headed back toward deep space, it accelerated slightly faster than it should have, based purely on the sun's gravity. Comets do this because they release gases that act like tiny rocket engines. But Oumuamua showed no signs of releasing gas. No tail, no cloud of material around it. Yet something was pushing it. Scientists proposed it might be outgassing something we could not see, or that sunlight was pushing against it like a solar sail, but neither explanation fit perfectly. One astronomer, Avi Loeb from Harvard, suggested it might be artificial, a light sail built by an alien civilization. The academic community mostly disagreed, preferring natural explanations, but the fact that a serious scientist from a prestigious institution would even propose this tells you how strange Oumuamua really is. And Oumuamua is not alone. There are planets out there with no star, rogue planets wandering through the galaxy in complete darkness. We have detected them through gravitational effects and occasional flashes when they pass in front of distant stars. These worlds drift through the void, frozen and lifeless, ejected from their home solar systems by gravitational interactions billions of years ago. Some estimates suggest there might be more rogue planets than stars in the galaxy. Trillions of orphaned worlds floating in the space between star systems. Some might even have moons with subsurface oceans heated by tidal forces, harboring life in absolute isolation from any sun. Then there are the hypervelocity stars. Stars moving so fast they are escaping the galaxy entirely. One star, US 708, is racing away at 1,200 kilometers per second. At that speed, it will leave the Milky Way and drift into intergalactic space forever. How does a star get moving that fast? The leading theory is that these are stars that once orbited too close to the supermassive black hole at the center of our galaxy. Their companion star got captured by the black hole and they got flung outward like a stone from a slingshot. But some hypervelocity stars do not seem to have come from the galactic center, and their origins remain unclear. Speaking of things that make no sense, astronomers have found enormous voids in space, not just empty regions, but vast bubbles where very few galaxies exist. The Bodas void is 330 million light years across and contains only about 60 galaxies when it should contain thousands. It is one of the largest known structures in the universe. Why would such a massive region have so little matter? Some think it formed from the merger of several smaller voids. Others wonder if it could be evidence of some unknown process in the early universe. Standing on a planet at the edge of the Bodas void and looking inward, you would see almost nothing, just darkness stretching in every direction for hundreds of millions of light years. And then there are the stars that simply vanish. The vanishing and appearing sources during a century of observations project compared old photographs of the sky taken decades ago with modern observations. They found stars that appear in old images but are completely gone now, not dimmed, not hidden, gone. Where did they go? Stars do not just disappear, they burn for millions or billions of years. Even when they die, they leave something behind: a white dwarf, a neutron star, a black hole, a supernova remnant. But these stars left nothing. It is as if they were erased. One possibility is that they were not stars at all, but brief, transient events we do not understand. Another is that they underwent some kind of failed supernova and collapsed directly into black holes without producing a visible explosion. Or maybe, just maybe, they were alien megastructures that have since been dismantled and moved. We do not know. The universe is full of things that should not be there, and things that should be there, but are not. Every time we build a better telescope, we find more anomalies, more exceptions to the rules, more mysteries hiding in the dark. Now we need to go smaller, much smaller, down to the level of atoms and beyond, where the rules of reality start to break down and the universe reveals itself to be far stranger than anyone could have imagined. In the early 1900s, physicists were trying to understand light. They knew it behaved like a wave because it could create interference patterns, but then they discovered it also behaved like a particle. This should not be possible. Something cannot be both a wave and a particle at the same time. But light did not care what we thought should be possible. Then came the double slit experiment, and everything got worse. Scientists fired individual photons, one at a time, at a barrier with two slits in it. If light was purely a particle, each photon would go through one slit or the other and hit the screen behind it in two distinct bands. But that is not what happened. Instead, the photons created an interference pattern, the kind of pattern you only get when waves overlap and cancel each other out. Each single photon somehow went through both slits at once, interfered with itself, and created a wave pattern on the screen. This made no sense. A single particle cannot be in two places at the same time, but it gets stranger. When scientists set up detectors to see which slit each photon actually went through, the interference pattern disappeared. The moment you try to observe which path the photon takes, it stops acting like a wave and starts acting like a particle. It is as if the photon knows it is being watched and changes its behavior accordingly. This is called the observer effect, and it has profound implications. It suggests that the act of measurement changes reality, that particles do not have definite properties until you observe them. Before you look, a photon exists in a superposition, traveling through both slits simultaneously. The moment you measure it, the superposition collapses and the photon becomes localized. Richard Feynman, one of the greatest physicists of the 20th century, said that nobody understands quantum mechanics, and he was right. We can use the math, we can make predictions that match experiments with incredible precision, but we have no idea what it actually means. Schrödinger tried to show how absurd this was with his famous thought experiment about a cat. Put a cat in a box with a device that has a 50% chance of releasing poison based on a quantum event like radioactive decay. Until you open the box and observe the outcome, quantum mechanics says the cat is in a superposition of both alive and dead at the same time. Only when you look does the wave function collapse and the cat become definitely one or the other. Obviously, no one believes a real cat can be both alive and dead. But if quantum superposition applies to particles, why not to larger objects? Where is the line between the quantum world and the everyday world? We do not know. Then there is quantum entanglement, which Einstein called spooky action at a distance. When two particles become entangled, they remain connected no matter how far apart they are. Measure the state of one particle, and you instantly know the state of the other, even if it is on the other side of the universe. Einstein hated this idea. He thought it violated the principle that nothing can travel faster than light. If measuring one particle instantly affects another particle billions of light years away, that seems like information is traveling faster than light. He believed there must be hidden variables, some underlying reality that determines the particle's states in advance. But experiments have proven Einstein wrong. The connection is real. Entangled particles really do influence each other instantaneously across any distance. Somehow the universe allows this instant correlation without actually sending information faster than light. How? Nobody knows. Quantum tunneling is another phenomenon that defies common sense. Particles can pass through barriers that they do not have enough energy to cross. Imagine throwing a ball at a wall. The ball does not have enough energy to go through, so it bounces back. But in the quantum world, there is a small probability that the ball will simply appear on the other side of the wall without ever going through it. This is not science fiction. Quantum tunneling is real and happens all the time. It is essential for the sun to shine. The temperatures and pressures inside the sun are not quite high enough for hydrogen nuclei to overcome their mutual electrical repulsion and fuse into helium. But quantum tunneling allows them to occasionally pass through the energy barrier, enabling nuclear fusion. Without quantum tunneling, stars could not exist. Then there is the delayed choice quantum eraser experiment, which somehow makes things even weirder. This experiment shows that you can change what happened in the past by making a measurement in the present. You can erase the information about which path a photon took after it has already hit the detector, and the interference pattern will reappear retroactively. It is as if the present can reach back and alter the past. Causality itself starts to break down at the quantum level. Some physicists interpret this through the many worlds theory. They say that every time a quantum measurement happens, the universe splits into multiple versions. In one version, the photon went through the left slit. In another version, it went through the right slit. All possible outcomes happen, each in its own separate universe. We just experience one branch of an endlessly dividing multiverse. Other physicists prefer the Copenhagen interpretation, which says that particles do not have definite properties until measured. Reality is fundamentally probabilistic. The wave function describes all possible states, and observation collapses it into one actual state. Still others think consciousness plays a role, that the universe needs an observer to become real. Without consciousness to collapse the wave function, everything remains in superposition. This raises the disturbing question of whether the universe existed before conscious beings evolved to observe it. There are also pilot wave theories, objective collapse models, and various other interpretations. After a century of quantum mechanics, physicists still cannot agree on what it means. And here is something that will keep you up at night. To never quantum immortality. It is a thought experiment based on the many worlds interpretation. Imagine you are in a quantum suicide machine that has a 50% chance of killing you based on a quantum measurement. In half of the resulting universes, you die, but in the other half, you survive. From your subjective experience, you will always find yourself in a universe where you survived. No matter how many times you pull the trigger, there will always be a branch of reality where you are still alive. From your perspective, you would be immortal, surviving against increasingly impossible odds, while in countless other universes, your copies have died. This is deeply unsettling. It suggests that your consciousness can never experience its own death. You will always find yourself in whatever branch of reality allows you to continue existing, watching everyone around you age and die while you inexplicably keep surviving. Of course, this is speculation built on an interpretation that might not be correct. But the fact that quantum mechanics even allows us to seriously consider such ideas shows how far we are from understanding the fundamental nature of reality. The quantum world does not make sense. It violates our intuitions about how things should work, and yet it is the foundation of everything. The entire universe runs on quantum mechanics. There is something happening inside your skull right now that science cannot explain. You are experiencing this moment. You are aware of these words, aware of your thoughts, aware of being you. This simple fact, The existence of subjective experience is one of the deepest mysteries in all of science. Philosophers call it the hard problem of consciousness, not how the brain processes information, not how neurons fire and communicate, but why there is something it feels like to be you. Why does the physical matter in your head produce an inner world of sensations, emotions, and thoughts? Why is there anyone home at all? We can study the brain in incredible detail. We can map every neuron, trace every connection, watch the electrical patterns that flow through it when you think or feel or remember. We can identify which regions activate when you see the color red, or hear a familiar song, or feel afraid. But none of that explains why you have a first person experience of redness or melody or fear. That computer can process information about the color red without experiencing redness. A camera can detect red light without knowing what red looks like. So why do you experience it? What is it about the particular way neurons are arranged in your brain that creates the subjective feeling of being conscious? Some scientists think consciousness emerges from complexity. Get enough neurons connected in the right way, and somehow awareness appears. But this does not really answer the question, it just moves it back a step. Why would complexity create experience? Plenty of complex systems exist that are not conscious. A weather system is complex. The economy is complex. Are they aware of anything? Others propose that consciousness is fundamental, like space or time or energy, that it exists at the most basic level of reality, and that brains do not create it, but rather tune into it, like a radio receiving a signal. This idea is called panpsychism, and while it sounds strange, some very serious philosophers and scientists take it seriously. Then there are the mysteries of what happens when consciousness seems to leave the body. Thousands of people who have been clinically dead and then revived report near death experiences. They describe similar things across different cultures and time periods: a sense of peace, moving through a tunnel, seeing a bright light, encountering deceased relatives. Some report floating above their bodies and observing the room where they died. Skeptics say these are hallucinations produced by a dying brain, oxygen deprivation, the release of endorphins, random neural activity. But some near death experiencers report specific details about what happened in the room while they were unconscious, things they could not have known if they were truly only hallucinating inside their own dying mind. In one famous case, a woman named Pam Reynolds underwent brain surgery that required her body to be cooled, and her heart stopped. Her brain activity was completely flat. She was as close to dead as you can be without actually dying. Yet when she was revived, she described seeing the surgical tools, hearing conversations between doctors, observing the operation from above, details that were later confirmed as accurate. Materialist scientists argue there must be some remaining brain activity we cannot detect, some minimal function that allows perception and memory formation, even when all our instruments show nothing. But the cases keep accumulating. People blind from birth, reporting visual near-death experiences, patients describing events that happened in other rooms while they were unconscious, children who have never been taught about near-death experiences describing the tunnel and the light without any cultural framework to draw from. Then there are out-of-body experiences that happen to people who are not dying, during sleep, during meditation, sometimes spontaneously. They report the same sensation of floating above their physical body, seeing themselves from outside. Some can apparently gather information from distant locations during these experiences. Controlled experiments have produced intriguing results, though nothing conclusive enough to convince mainstream science. The brain itself presents paradoxes we cannot resolve. Consider the binding problem. When you look at a red apple, different parts of your brain process different features. One area handles color, another handles shape, another handles motion, another handles the memory of what an apple is. These processes happen in physically separate locations, yet you experience a unified whole. You do not see redness in one place and roundness in another. You see a red round apple, all bound together into a single coherent perception. How does the brain bind all these separate processes into unified consciousness? Where does the integration happen? We do not know. There is no central location in the brain where everything comes together. It is distributed across the whole structure, yet your experience is unified. And then there is anesthesia. Doctors use it every day in operating rooms around the world, and we have no idea how it works. We know which drugs turn consciousness off and which ones turn it back on. We can measure their effects on neural activity, but we do not understand the mechanism by which these chemicals abolish awareness. Various anesthetics have completely different chemical structures and act on different receptors in the brain, yet they all somehow produce the same end result. Consciousness vanishes. You go from being fully aware to experiencing nothing, with no memory of the time that passed. How do such diverse chemicals all converge on the same outcome? What are they disrupting? What is the switch they are flipping? Some researchers think anesthetics disrupt quantum processes in the microtubules inside neurons. Others believe they interfere with the electromagnetic field that the brain generates. Still others focus on how they affect the communication between different brain regions. But the honest answer is we do not know. Dreams add another layer of mystery. Every night you fall asleep and your brain constructs entire worlds. You inhabit a dream body in a dream environment, interacting with dream people, experiencing dream emotions that feel completely real until you wake up. There are theories. Dreams might help consolidate memories, transferring information from short term to long term storage. They might allow the brain to practice responding to threats in a safe environment. They might be a way of processing emotions or solving problems. But none of these theories fully explain the bizarre nature of dreams. Why are they so surreal? Why do they violate the laws of physics? Why can you fly, teleport, or suddenly find yourself in impossible situations without questioning it until you wake? And what about lucid dreams, where you become aware that you are dreaming while still inside the dream? In a lucid dream, you can control the environment, make decisions, explore a world that feels as vivid as waking reality. Some people can reliably induce lucid dreams. They can communicate with researchers through eye movements while dreaming. They can perform tasks inside dreams that correspond to real brain activity patterns. It is consciousness operating in a completely self-generated reality. The placebo effect remains equally mysterious. Give someone a sugar pill, but tell them it is a powerful painkiller, and their pain actually decreases, not because they think it does, actually decreases measurably. Their brain releases endorphins. Inflammation goes down. Healing speeds up. The effect is so powerful that pharmaceutical companies have to test new drugs against placebos because the placebo itself often produces significant results. In some studies, fake knee surgery works almost as well as real knee surgery. Patients whose knees were just cut open and sewn back up without any actual repair showed similar improvement to patients who received legitimate surgical intervention. How does belief change physical reality? How does the expectation of healing trigger actual biological healing processes? The mind is affecting the body in ways we cannot explain. Then there is the origin of self awareness itself. At some point in evolution, organisms became aware that they were aware. They developed a sense of self, an inner narrator, an eye that observes and reflects on its own existence. When did this happen? How did it happen? What evolutionary advantage does self awareness provide? Some animals clearly have it. Primates pass the mirror test, recognizing their own reflection. Elephants and dolphins show signs of self awareness. But where is the line? Do dogs have an inner experience of being a dog? What about fish? What about insects? Is there something it is like to be an ant? Or are they just biological machines operating without any inner life? And here is perhaps the most disturbing mystery of all: split brain patients. When the connection between the two hemispheres of the brain is severed to treat severe epilepsy, something very strange happens. The left hemisphere can speak, the right hemisphere cannot, but both hemispheres can process information and make decisions independently. Show a split brain patient an image to only their right hemisphere, and they cannot verbally say what they saw because the speech center is in the left hemisphere, but they can draw it with their left hand, which the right hemisphere controls. Show them two different images, one to each hemisphere, and ask them to point to related objects, and each hand points to something different. This raises a terrifying question. Are there two consciousnesses inside a split brain patient? Two separate centers of awareness, each experiencing its own version of reality? And if cutting the connection between hemispheres creates two consciousnesses, were there always two that were just sharing information? Are you actually multiple consciousnesses that are so interconnected you experience yourself as one? These questions do not have answers. Consciousness remains the greatest mystery of all. We are using consciousness to try to understand consciousness, and that might be an impossible task. It is like trying to see your own eyes without a mirror. The tool and the object of study are the same thing. Time is the most familiar thing in your life. You have experienced every single moment of your existence within it: past, present, future, cause and effect, before and after. It seems obvious, fundamental, undeniable, and yet time might be the biggest illusion of all. Physics treats time very differently than our everyday experience suggests. In Einstein's equations, time is just another dimension, like the three dimensions of space. The past, present, and future all exist equally. They are just different locations in space-time. When you move through space, you move through time. When gravity warps space, it also warps time. Near a black hole, time slows down relative to distant observers. Fall toward the event horizon, and from your perspective, time seems normal, but to someone far away, you appear to freeze, taking infinite time to actually cross the boundary. Which perspective is correct? Both are. Time is relative, different for different observers. This creates paradoxes. Imagine two twins. One stays on Earth. The other travels to a distant star at nearly the speed of light. then returns. Because of time dilation, less time passes for the traveling twin. They come back younger than their sibling, who stayed home. This is not a thought experiment. It is real physics, confirmed by precise atomic clocks on airplanes and satellites. But here is the puzzle. Time always moves forward, entropy always increases, disorder always grows. You can scramble an egg, but you cannot unscramble it. You can shatter a glass, but the pieces never spontaneously reassemble. The past is fixed. The future is open. There is a clear arrow pointing from past to future. Yet the fundamental laws of physics are time symmetric. If you filmed particles interacting and played the video backward, the backward motion would obey all the same laws as the forward motion. At the quantum level, processes work just as well in reverse. So why does time have a direction at the macroscopic level? The answer seems to involve entropy and the second law of thermodynamics. The universe started in a very low entropy state at the Big Bang, incredibly ordered and organized. Over time, entropy increases, systems become more disordered, and that increase in entropy gives time its arrow. We remember the past and not the future because memories are low entropy structures. We perceive cause and effect because effects are higher entropy than causes. But this just pushes the mystery back. Why did the universe start in such a low entropy state? Why was the Big Bang so organized? If you rewind the universe back to the beginning, everything gets more and more ordered until you reach the initial singularity, which somehow contained all the matter and energy of the universe in an infinitesimally small point. That is the lowest entropy state imaginable. Why? What set up those initial conditions? Some physicists think time itself might not be fundamental. Carlo Rovelli argues that time emerges from more basic properties of the universe, that at the deepest level, time does not exist. The equations of quantum gravity do not contain time as a variable, only change, only relationships between events. Our experience of flowing time might be an illusion created by our limited perspective. Then there are closed time-like curves, solutions to Einstein's equations that allow for loops in time. If space-time can be warped enough, you could theoretically travel along a path through space that brings you back to your own past, not traveling backward in time, but moving forward along a curved path that loops back. Rotating black holes might create such paths. Wormholes, if they exist and can be stabilized, might allow travel between different points in spacetime, potentially including travel to the past. But this creates the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, you could not travel back in time to prevent your grandfather from meeting your grandmother, so you would be born after all. The paradox loops endlessly. Some physicists resolve this with the many worlds interpretation. When you travel back and change the past, you create a new timeline, a branch of reality where you were never born, but your original timeline still exists. You just cannot return to it. Other physicists think consistency is enforced by the universe. If you try to change the past, events will conspire to prevent you from doing so. You become part of the past that already happened, unable to alter it. Or maybe time travel to the past is simply impossible. Maybe the laws of physics contain some undiscovered principle that prevents closed time-like curves from ever forming, protecting causality from violation. We do not know. Quantum mechanics adds its own temporal strangeness. Experiments in quantum mechanics show what looks like retrocausality, where the future affects the past. The delayed choice quantum eraser experiment demonstrates that a measurement you make now can determine what happened to a particle earlier, even though the earlier event is already over. It is as if information can flow backward in time at the quantum level. Then there are time crystals, a bizarre phase of matter discovered in recent years. Normal crystals have a repeating structure in space, atoms arranged in regular patterns. Time crystals have a repeating structure in time. They oscillate between different states perpetually without consuming energy, breaking the normal symmetry of time. In standard physics, if a system is in its lowest energy state, its ground state, it should not change over time. It should just sit there, static. Time crystals violate this. They change periodically, even in their ground state, creating a kind of motion through time that does not require energy input. How is this possible? The discovery challenges our understanding of equilibrium and thermodynamics. And what about the nature of the present moment? The now that you are experiencing right now? How long does the present last? Is it an instant with zero duration? But how can you experience something with zero duration? Is it a fraction of a second? But then which fraction? Different senses process information at different speeds. Vision takes longer than hearing. Does each sense have its own present moment? Neuroscience suggests that your experience of now is actually assembled by your brain from sensory information that arrived at slightly different times. Your brain collects inputs, processes them, and then presents you with a coherent picture of the present that actually represents events that happened a fraction of a second ago. You are always living slightly in the past, experiencing a construction your brain created from delayed signals. Some philosophers argue that the present does not exist at all. The past is fixed, determinate, unchangeable. The future is open, undetermined, full of possibility. The present is the infinitesimally thin boundary between them, a mathematical point with no duration. And if it has no duration, then it does not exist as an actual moment you can inhabit. You are either remembering the past or anticipating the future, but never truly experiencing the present. Others say the present is all that exists. The past is gone, vanished, nothing but memories and records. The future has not happened yet and might never happen in the way you anticipate. Only the present is real. Only now exists. But if only now exists, and now is constantly changing, then reality itself is constantly being created and destroyed, coming into being and passing away moment by moment. Einstein wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. From the perspective of relativity, all moments in time exist equally. The universe is a four-dimensional block where every event that has ever happened or will ever happen exists eternally. You do not move through time. You are a four-dimensional object extended through time, and your consciousness just illuminates different slices of that object as it moves along your world line. But if that is true, if all moments exist equally, then everything is predetermined. The future already exists in the block universe, fixed and unchangeable, just like the past. Free will becomes an illusion. Your choices have already been made, already exist in the future sections of space-time, and you are just becoming aware of them as your consciousness slides along the predetermined path. This contradicts quantum mechanics, which is fundamentally probabilistic. The future is not determined until wave functions collapse and possibilities become actualities. So, which view is correct? Is the future fixed or open? Does time flow, or do we move through it? Is time even real? And here is a final unsettling thought. What existed before time began? Before the Big Bang, the question might be meaningless, because before implies time, and time started at the Big Bang. There is no before. But that answer does not satisfy. Something caused the Big Bang. Something existed in whatever state reality was in when there was no time. What was that? How can we even think about it when every concept we have is embedded in time? Time is supposed to be simple. It passes 1 second per second, forward, never backward. But the closer you look, the less sense it makes. And that should make you wonder what else about reality is far stranger than it appears. 13.8 billion years ago, everything began. Space, time, matter, energy, all of it erupted from a single point smaller than an atom. In a fraction of a second, the universe inflated from nothing into a region larger than a galaxy. This is what we call the Big Bang, and it is the origin story that science gives us. But it does not answer the deepest question: why is there something instead of nothing? Think about that. Nothingness is simpler than existence. No space, no time, no energy, no laws of physics, just absolute nothing. That should be the default state. Why should anything exist at all? Why should there be a universe rather than an eternal void? Some physicists argue that nothing is unstable, that quantum mechanics allows for fluctuations in the void, and that these fluctuations can spontaneously create universes. Lawrence Krauss famously wrote a book titled A Universe from Nothing, arguing that quantum fields contain energy even in empty space, and that this vacuum energy can produce particles and even entire universes. But critics point out that quantum fields are not nothing, they are something. They have properties, they follow laws, they exist in some sense. So the question just moves back a level. Why do quantum fields exist? Why do the laws of physics exist? Why is there something rather than nothing? Perhaps there is no answer. Perhaps existence is just a brute fact, something that simply is without explanation. Or perhaps our question is flawed, based on assumptions that do not apply to reality at its most fundamental level. Assuming the universe did begin with the Big Bang, other mysteries immediately arise. One is the matter-antimatter asymmetry. According to the standard model of particle physics, the Big Bang should have created equal amounts of matter and antimatter, and when matter and antimatter meet, they annihilate each other in a burst of energy. So the early universe should have contained equal parts matter and antimatter. They should have collided and destroyed each other, and the universe should now contain nothing but photons. No atoms, no stars, no planets, no you, and yet here we are, made of matter, surrounded by matter, with almost no antimatter anywhere. Something broke the symmetry. Some process created slightly more matter than antimatter. For every billion antimatter particles, there were 1,000,000,001 matter particles. Everything annihilated except that tiny excess of matter, and that excess became everything we see. but we do not know what caused the imbalance. Some unknown physics in the first moments of the universe violated the symmetry between matter and antimatter, and without that violation, nothing would exist. Then there is the horizon problem, the cosmic microwave background, the afterglow of the Big Bang, has almost exactly the same temperature in every direction. It varies by only a few parts in 100,000. This means that regions of space on opposite sides of the universe, regions that are so far apart that light has never had time to travel between them, somehow have the same temperature. How is that possible? How did these disconnected regions reach thermal equilibrium? It is like finding that two pots of water on opposite sides of the earth have exactly the same temperature, even though they have never been connected. They should be different temperatures. There should be no way for them to equalize. The leading solution is cosmic inflation, the idea that in the first fraction of a second, the universe expanded exponentially fast, much faster than the speed of light. Before inflation, the entire observable universe was a tiny region where everything was in contact and could reach equilibrium. Then inflation stretched that tiny region into a volume larger than what we can see today. Inflation solves the horizon problem and several other cosmological puzzles. It explains why the universe is so flat, why it is so uniform, why we do not see magnetic monopoles or other exotic particles that should have been produced in the Big Bang. But inflation also creates new problems. What caused inflation to start? What caused it to stop? What is the inflatone field that supposedly drove the expansion? We have some mathematical models, but no confirmed theory, and inflation predicts that the process should be eternal. Once it starts in one region, quantum fluctuations create new regions where inflation continues, and those regions create more regions, and so on forever. This eternal inflation leads to an infinite multiverse of bubble universes, each with potentially different laws of physics. If that is true, then everything that can happen does happen somewhere in the multiverse. There are infinitely many versions of you living infinitely many different lives. There are universes where the laws of physics are slightly different, where electrons are heavier or the force of gravity is stronger. Most of these universes would be sterile, unable to form stars or planets or life. But in the infinite multiverse, every possibility is realized. This brings us to the fine-tuning problem. The laws of physics contain certain constants, numbers that determine how strong various forces are, how massive particles are, how fast light travels. These constants seem arbitrary. As far as we know, they could have been different, but if they were even slightly different, life could not exist. If the strong nuclear force were a few percent weaker, atomic nuclei would not hold together and there would be no complex atoms. If it were a few percent stronger, stars would burn too fast for life to evolve. If gravity were slightly stronger, stars would collapse into black holes before planets could form. If it were slightly weaker, galaxies would never condense from the primordial gas. The cosmological constant, the energy density of empty space, is fine-tuned to an absurd degree. If it were much larger, the universe would have expanded so fast that galaxies could never form. If it had the opposite sign, the universe would have collapsed back on itself immediately after the Big Bang. The value we measure is incredibly close to zero, but not quite zero, balanced perfectly to allow structures to form. Why are the constants fine-tuned for life? One answer is the anthropic principle. We observe these particular values because if they were different, we would not be here to observe anything. The universe has the constants it has because only universes with these constants can produce observers. It is a selection effect. If the multiverse is real, then every possible combination of constants exists somewhere, and we inevitably find ourselves in one of the rare universes where the constants allow life. But this explanation feels unsatisfying to many physicists. It means we can never predict the constants from deeper principles. They are just random environmental accidents. Other scientists think the constants are not arbitrary, that some undiscovered theory will show that they have to have the values they have. String theory, for example, attempts to derive all the constants from the geometry of extra dimensions, but string theory has its own problems and remains unconfirmed. Then there is the singularity at the beginning. General relativity predicts that if you run the expansion of the universe backward, everything converges to a point of infinite density and infinite temperature where the laws of physics break down. The singularity is not a place in space, it is the beginning of space itself. Before it, there was no before. But infinity usually signals that your theory has gone wrong. Most physicists think the singularity is not real, but rather an indication that general relativity fails at extreme conditions. A complete theory of quantum gravity should describe what actually happens at the moment of the Big Bang without running into infinities. Loop quantum gravity suggests that the universe might have bounced, that before the Big Bang, there was a previous contracting universe that reached a minimum size and then rebounded into our expanding phase. String theory offers other possibilities, including colliding brains in higher dimensional space. But these are speculations. We have no observational evidence for what happened at the absolute beginning. And maybe there was no absolute beginning. Maybe the universe is cyclic, expanding and contracting eternally. Or maybe it is part of a larger structure that has always existed. Maybe time itself does not apply to whatever gives rise to universes. The deepest question remains unanswered. Why does anything exist? Why is there a universe rather than nothing? Why are there laws of physics rather than chaos? Why is reality structured in a way that allows complexity and consciousness to emerge? Science can trace the history of the universe back to a fraction of a second after the Big Bang. It can explain how matter formed, how stars ignited, how galaxies assembled, but it cannot explain why there is a universe to have a history in the first place. Some people turn to philosophy or religion for answers. God created the universe. Being itself is self-existent. Reality is necessary rather than contingent. But these answers just rename the mystery rather than solving it. The origin of everything is the ultimate unknown, and standing on this tiny planet, made of stardust, conscious for a brief moment in cosmic history, we look back at the beginning and forward to the end and wonder what it all means. 4 billion years ago, Earth was a hellish place. Volcanoes erupted constantly. The atmosphere was toxic. Asteroids slammed into the surface with devastating force. The oceans were hot and acidic, and yet somehow, in this violent chaos, something extraordinary happened. Life began. We do not know how. We can trace the evolution of species back through time, watching as complexity emerged from simplicity, as mammals arose from reptiles, as fish crawled onto land, as multicellular organisms evolved from single cells. But when we reach that first cell, that first self replicating organism, the trail goes cold. The problem is chemistry. Living things are made of proteins, and proteins are made by reading instructions encoded in DNA. But DNA is also a protein. It requires other proteins to replicate itself. So, which came first? You cannot have DNA without proteins to build it, but you cannot have proteins without DNA to encode them. It is a chicken and egg problem at the molecular level. Scientists have proposed that RNA came first. RNA can both store information like DNA and catalyze chemical reactions like proteins. In theory, an RNA world could have existed where RNA molecules replicated themselves without needing DNA or proteins. But creating self replicating RNA in the lab has proven incredibly difficult. The molecules tend to fall apart or bind to each other incorrectly. Getting them to spontaneously form and replicate requires very specific conditions that might not have existed on early Earth. And even if RNA could self replicate, how did it first form? RNA is a complex molecule. It requires sugars, phosphates, and nucleotide bases all coming together in precise arrangements. The odds of this happening by random chance are astronomically small. Some researchers think life began near hydrothermal vents on the ocean floor, where heat and minerals could drive chemical reactions. Others think it started in shallow pools that went through cycles of wetting and drying, concentrating organic molecules. Some even suggest that life did not originate on Earth at all, but came from space on meteorites. We have found organic molecules in meteorites, amino acids and sugars that form in space and survive the journey to Earth's surface. Panspermia, the idea that life spreads from planet to planet through space, is a real hypothesis, but it just moves the question elsewhere. If life came from space, how did it start there? Once the first cell existed, evolution could begin. But then we hit another mystery. For billions of years, life remained simple. Single-celled organisms dominated. Then about 540 million years ago, during a period called the Cambrian explosion, complex life suddenly appeared everywhere. In just a few million years, most major animal groups emerged in the fossil record. Creatures with shells, with eyes, with segmented bodies, with every kind of basic body plan we see today. Why did it happen so fast? What triggered the sudden burst of diversity? Scientists have theories involving oxygen levels rising, genetic innovations like the development of Hox genes that control body plans, or ecological factors like predator-prey arms races, but none fully explain why complexity was delayed for so long and then erupted so quickly. And speaking of sudden events, there have been 5 major mass extinctions in Earth's history. The most famous killed the dinosaurs 66 million years ago when an asteroid struck the Yucatan Peninsula. But the worst happened 252 million years ago at the end of the Permian period. Over 90% of species went extinct. Life nearly ended completely. What caused it? Evidence points to massive volcanic eruptions in Siberia that lasted for thousands of years, releasing enormous amounts of carbon dioxide and sulfur dioxide into the atmosphere. The planet warmed dramatically. The oceans became acidic and lost oxygen. But some scientists think the volcanism was itself triggered by an asteroid impact on the opposite side of the planet. The shock waves from the impact could have focused on the far side and created the volcanic activity. We are still piecing together what happened. After each mass extinction, life rebounded and diversified again. New species evolved to fill empty niches, but the recovery took millions of years. These events reset evolution, creating opportunities for different groups to dominate. Without the extinction that killed the dinosaurs, mammals might never have become the dominant land animals. Humans might never have evolved. Which brings us to another deep mystery. Why do we age? Aging is not inevitable. Some organisms do not do it. Certain jellyfish can revert to earlier life stages and essentially live forever. Lobsters show no signs of aging and can live for over a century. Trees can live for thousands of years. So, why do humans age and die? The evolutionary explanation is that natural selection stops caring about you once you have reproduced and raised your offspring. Mutations that cause problems late in life are not selected against because you have already passed on your genes. So harmful mutations accumulate, repair mechanisms break down, and aging happens. But this does not fully explain why aging evolved in the first place. Some organisms invest heavily in maintenance and live a long time. Others burn fast and die young. The strategy depends on the environment and the species. In theory, if natural selection favored it, organisms could maintain their bodies indefinitely. The fact that most do not suggests there are trade offs between reproduction and longevity, between growing fast and living long. At the cellular level, aging involves telomeres shortening, mitochondria becoming less efficient, proteins misfolding and accumulating, DNA damage building up. But we do not fully understand why these processes are not repaired. Our cells have mechanisms to fix DNA, to clear out damaged proteins, to regenerate mitochondria. Why do these mechanisms fail over time? Then there is consciousness in non human animals. We know that we are conscious. We assume other humans are conscious because they report having inner experiences similar to ours. But what about dogs? They certainly seem to have feelings, to experience pain and pleasure, to form memories and recognize individuals. But is there really something it is like to be a dog? Or are they sophisticated biological machines responding to stimuli without any inner life? The question becomes harder as we move further from mammals. Birds show remarkable intelligence. Crows can solve complex puzzles, use tools, recognize human faces, even hold grudges. Parrots can learn hundreds of words and seem to understand concepts like color and shape. Are they conscious? Octopuses present an even stranger case. They are mollusks, more closely related to clams than to us. Their brains evolved completely independently from vertebrate brains. They have neurons distributed throughout their arms, which can move independently and make decisions without input from the central brain. An octopus can solve mazes, recognize individuals, use tools, change color to match their surroundings, and communicate emotions. Are they conscious? If so, what is it like to have consciousness distributed across 8 semi autonomous limbs? Fish were long thought to be simple stimulus response machines, but research now shows they have long term memories, can feel pain, can learn from observation, can recognize themselves in mirrors. The more we study them, the more complex their inner lives appear. Even insects might have some form of experience. Bees can count, learn abstract concepts, communicate the location of food sources through elaborate dances. Fruit flies seem to exhibit emotions, showing states that look like fear or frustration. Are they conscious in any meaningful sense? Plants present the most challenging question. They have no brains, no neurons, no nervous system, yet they respond to their environment in sophisticated ways. They communicate through chemical signals in the air and through fungal networks in the soil. When one tree is attacked by insects, it releases chemicals that warn neighboring trees, which then increase their own defenses. Trees seem to recognize their offspring and share resources with them preferentially. Some plants can even count, tracking the number of times they have been touched before responding. Is this intelligence? Is there any awareness involved? Or is it all just mechanistic chemical reactions? We cannot ask a plant what it experiences. We can only observe behaviors that seem far more complex than simple reflexes. The Fermi paradox haunts all discussions of life. If life arises easily wherever conditions are right, then the universe should be teeming with civilizations. Our galaxy alone contains hundreds of billions of stars. Many have planets. Many of those planets are inhabitable zones where liquid water can exist. If even a tiny fraction develop life, and a tiny fraction of those develop intelligence, and a tiny fraction of those develop technology, there should still be millions of technological civilizations in our galaxy. So where are they? Why have we detected no signals? Why do we see no signs of megastructures or engineered stars or any evidence of intelligence reshaping the cosmos? The silence is deafening. Maybe life is extremely rare. Maybe the jump from chemistry to biology requires such unlikely circumstances that it almost never happens. Maybe intelligence is rare. Maybe technology is rare. Maybe civilizations destroy themselves shortly after developing technology. Maybe they exist but cannot communicate across interstellar distances. Maybe they are already here and we do not recognize them. Maybe they have no interest in contacting us. Every explanation for the Fermi paradox is either disturbing or profound. Either we are alone, which seems impossible in such a vast universe, or we are not alone, but something prevents contact, which raises questions about what awaits us as we become more advanced. Life remains fundamentally mysterious. We do not know how it starts. We do not know why it became complex when it did. We do not know where consciousness begins or ends in the tree of life. We do not know if we are alone in the universe or surrounded by others we cannot perceive. And every living thing on Earth, from bacteria to blue whales, shares the same basic biochemistry, the same genetic code, the same fundamental molecular machinery. This suggests we all descend from a single origin, one lucky accident 4 billion years ago that gave rise to everything. But it also means we have only one example of life. We do not know if life elsewhere would be similar or completely different based on different chemistry, different molecules, different principles entirely. Beneath your feet right now, thousands of kilometers down, the Earth has a core made mostly of iron. It spins slightly faster than the rest of the planet, generating a magnetic field that protects us from solar radiation and cosmic rays. Without this magnetic field, the solar wind would strip away our atmosphere and sterilize the surface. Mars lost its magnetic field billions of years ago, and look what happened to it. But here is the strange part. Every few 100,000 years, The magnetic field reverses. North becomes south. South becomes north. The last reversal happened 780,000 years ago. We are overdue for the next one. During a reversal, the magnetic field weakens dramatically before reorganizing itself in the opposite direction. This process can take thousands of years. During that time, the protection from cosmic radiation diminishes. Some scientists think past reversals coincide with mass extinctions, though the evidence is debated. We do not fully understand what causes reversals. They seem to be related to changes in the flow of molten iron in the outer core, but the exact mechanism remains unclear. The Earth's magnetic field is generated by a geodynamo, convection in the liquid metal driven by heat from the solid inner core. Small changes in this convection can flip the entire field. Some researchers think we are currently in the early stages of a reversal. The magnetic North Pole has been moving rapidly across the Arctic in recent decades, accelerating from about 15 kilometers per year to about 55 kilometers per year. The field strength has decreased by about 10% over the last 170 years. These could be signs of an impending flip, or they could just be normal fluctuations. We do not have enough data to know. Then there is the mystery of how the moon formed. For a long time, scientists thought it might have been captured by Earth's gravity as it wandered through space, or that it formed alongside Earth from the same cloud of material, or that it split off from a rapidly spinning early Earth. None of these theories worked. The moon's composition is too similar to Earth's crust, but lacks the iron core Earth has. Then, in the 1970s, computer simulations suggested a dramatic origin. A Mars-sized object called the Tedia collided with Earth about 4.5 billion years ago. The impact was so violent it vaporized the Tedia and ejected enormous amounts of material from Earth's mantle into orbit. This debris eventually coalesced into the moon. The giant impact hypothesis explains many features: why the moon lacks a large iron core, why its composition matches Earth's mantle, why the Earth-Moon system has so much angular momentum, but it creates new questions. Where did the Rhea come from? Why did it hit Earth at just the right angle and speed to create the moon rather than destroying Earth or merging completely? Computer models show that only very specific impact parameters produce a moon. We got extremely lucky. And where did Earth's water come from? The water is essential for life, but Earth formed in the inner solar system where temperatures were too high for water ice to condense. The water we have now must have arrived later, delivered by asteroids or comets from the outer solar system after the planet cooled. But measurements of the hydrogen isotopes in Earth's oceans do not match most comets. They match certain types of asteroids better. This suggests that most of our water came from rocky bodies rather than icy ones. But those asteroids would have formed beyond the snow line, the boundary in the early solar system where water ice could exist. How did they end up in the inner solar system to collide with Earth? The NICE model proposes that the giant planets migrated early in the solar system's history. Jupiter moved inward, then was pulled back outward by Saturn. This migration disrupted the asteroid belt and sent countless objects flying through the inner solar system. Some collided with Earth, delivering water, but the details remain uncertain. Meanwhile, deep inside Earth, we are not entirely sure what the core is made of. We know it is mostly iron with some nickel, but seismic waves passing through the core behave in ways that suggest the presence of lighter elements mixed in, possibly silicon, oxygen, sulfur, or carbon. We cannot directly sample the core, so we rely on indirect evidence from seismology, mineral physics experiments, and models. The exact composition remains a subject of active research. Predicting earthquakes has turned out to be impossible. We know where earthquakes are likely to occur along fault lines. We know the statistics of how often large quakes happen in a given region, but we cannot predict when a specific earthquake will strike with any useful precision. The problem is complexity. An earthquake is a sudden release of stress that is built up over time as tectonic plates grind against each other. Small tremors can either relieve stress or trigger larger quakes. The Earth's crust is full of fractures and weak points. A tiny difference in initial conditions can lead to vastly different outcomes. It is a chaotic system, sensitive to details we cannot measure. Scientists have tried monitoring various precursor signals, changes in groundwater levels, electromagnetic anomalies, unusual animal behavior. Some researchers claim to have found correlations, but when tested rigorously, these methods fail to predict earthquakes reliably. The hope of giving people days or hours of warning before a major quake remains unfulfilled. Ball lightning is another phenomenon that defies explanation. People report seeing glowing spheres, usually the size of a basketball, floating through the air during thunderstorms. These spheres can pass through walls, move against the wind, and sometimes explode with a loud bang. They have been observed for centuries, reported by reliable witnesses, including scientists, but remain poorly understood. Most scientists accept that ball lightning is real, but no one knows what it is. Some theories propose that it is a plasma held together by magnetic fields. Others suggest it involves silicon nanoparticles ignited by lightning strikes on soil. Still others think it might be a type of microwave or Maser phenomenon. Laboratory experiments have produced glowing spheres that last a few seconds, but nothing that fully reproduces the behavior described in reports. The Bermuda Triangle has achieved legendary status as a place where ships and planes mysteriously vanish. The reality is less dramatic. Statistical analysis shows that the Bermuda Triangle has no higher rate of disappearances than any other heavily traveled region of ocean. Many of the famous cases involve exaggerations, errors, or have mundane explanations. But the ocean does hold real mysteries. Massive rogue waves, waves up to 30 meters high that appear suddenly in open water, were once dismissed as sailor myths. Then in 1995, instruments on an oil platform measured a wave 25.6 meters high in conditions where the surrounding waves were much smaller. Since then, satellites and buoys have confirmed that rogue waves are real and more common than expected. How they form is still debated. Constructive interference of normal waves, focusing by ocean currents, we are still learning. Magnetic anomalies exist all over Earth, places where the magnetic field is stronger or weaker than expected. Some are explained by deposits of magnetic minerals in the crust. Others remain mysterious. The Kursk magnetic anomaly in Russia is one of the largest, caused by enormous iron ore deposits. But there are smaller anomalies with no obvious geological explanation. Ancient magnetic anomalies preserved in rocks show that the magnetic field has not only reversed, but also varied wildly in strength over geological time. Sometimes it was much stronger than today. Other times it nearly vanished. These variations affected how much cosmic radiation reached the surface, potentially influencing evolution and climate. The Younger Dryas is a period about 12,900 years ago, when the Earth suddenly plunged back into Ice Age conditions. For thousands of years, the planet had been warming up after the last glacial maximum. Then temperatures dropped sharply and stayed cold for over 1,000 years before warming resumed. What caused this sudden climate shift? The leading theory is that a massive influx of fresh water from melting ice sheets disrupted ocean circulation in the North Atlantic. Without the Gulf Stream bringing warm water north, Europe and North America froze. But where did the fresh water come from? Glacial Lake Agassiz, a huge lake formed by melting ice in North America, might have suddenly drained into the ocean. More controversially, some researchers propose that a comet or asteroid impact triggered the Younger Dryas. They point to a layer of sediment from that time containing high levels of platinum, nanodiamonds, and spherules that could be impact debris. Critics argue that the evidence is not strong enough and that non impact processes can explain the findings. The debate continues. And then there is Saturn's hexagon. At Saturn's north pole, there is a persistent cloud pattern in the shape of a perfect hexagon. Each side is about 13,800 kilometers long. The hexagon rotates with the planet and has been stable for decades, observed first by Voyager in the 1980s and later by Cassini. Why a hexagon? Fluid dynamics can produce geometric patterns under certain conditions. Laboratory experiments have created hexagonal patterns in rotating fluids, but the precision and stability of Saturn's hexagon are remarkable. The mechanism involves jet streams at different latitudes interacting in ways that create standing wave patterns, but the exact details of why it forms a hexagon rather than some other shape are still being worked out. Earth and the solar system hold countless puzzles. We live on a planet we are still discovering. Beneath our feet, in our oceans, in our atmosphere, mysteries persist, and looking out at the other worlds in our cosmic neighborhood, we find even more strangeness. Each answer reveals new questions. Each discovery reminds us how much we do not know. There is a question that has haunted mathematicians for over 160 years. It seems simple at first. Take all the whole numbers and ask which ones are prime. A prime number can only be divided by 1 and itself. 2, 3, 5, 7, 11, 13. They seem scattered randomly through the number line with no obvious pattern. But there is a pattern hidden in them. Bernhard Riemann discovered that the distribution of prime numbers is connected to a mathematical function called the Riemann zeta function. This function produces complex numbers, numbers that have both a real and an imaginary component. When you plot where this function equals 0, you get points in the complex plane. Riemann noticed that all the interesting zeros seemed to line up on a single line. He conjectured that all non-trivial zeros of the zeta function have a real part equal to 1/2. If true, this tells us deep truths about how prime numbers are distributed. It connects number theory to physics, to quantum mechanics, to chaos theory. Thousands of mathematicians have tried to prove the Riemann hypothesis. Computers have verified it for trillions of zeros, but no one has proven it for all zeros. It remains one of the most important unsolved problems in mathematics. A proof would win you $1 million prize and eternal fame. But more than that, It would reveal why numbers behave the way they do. Then there is P versus NP, a question about the nature of computation itself. Some problems are easy to solve. Adding numbers, sorting a list, you can write an algorithm that solves them quickly. These are called P problems, problems solvable in polynomial time. Other problems are hard to solve, but easy to check. Finding the factors of a large number takes a long time, but if someone gives you the factors, you can quickly multiply them together to verify they are correct. These are called NP problems, problems whose solutions can be verified in polynomial time. The question is whether P equals NP. Is every problem that is easy to check also easy to solve? Or are there problems where checking a solution is fundamentally easier than finding it? Most mathematicians believe P does not equal NP. If it did, it would mean that any problem whose solution you can verify quickly can also be solved quickly. Cryptography would break. Password systems would be useless. Computers could quickly solve problems we currently think are intractable, but no one has proven it. The question touches on the limits of computation, on what is fundamentally knowable through calculation. It asks whether creativity, insight, and intuition are necessary for certain types of problems, or whether brute force algorithms could eventually solve anything. Kurt Gödel proved something shocking in 1931. He showed that any sufficiently complex mathematical system contains statements that are true but cannot be proven within that system. There are mathematical truths that exist beyond proof. This is Gödel's incompleteness theorem, and it shattered the dream of a complete and consistent mathematics. It means there are limits to formal reasoning. Some questions can never be answered by following logical rules. You need to step outside the system, add new axioms, expand your framework, but then your new expanded system will also contain unprovable truths. Mathematics, the most precise and certain form of knowledge we have, is incomplete. There are mathematical facts we can never prove. This has profound implications for any system based on logic and rules, including computers and possibly the human mind. Infinity creates endless paradoxes. Hilbert's Hotel is a thought experiment about a hotel with infinitely many rooms, all occupied. A new guest arrives. Can you accommodate them? Yes. Move the guest in room 1 to room 2. Move the guest in room 2 to room 3, and so on. Every guest moves to the next room. Now room 1 is empty for the new guest. Infinitely many new guests arrive. Can you accommodate them? Yes. Move the guest in room 1 to room 2. Move the guest in room 2 to room 4. Move the guest in room 3 to room 6. Every guest moves to a room with twice their room number. Now all the odd-numbered rooms are empty. Infinitely many rooms available for infinitely many new guests. Infinity does not behave like normal numbers. You can add to it, subtract from it, rearrange it, and it remains infinite. This causes problems in physics. When calculations produce infinite results, it usually means the theory has broken down. Renormalization techniques can remove infinities from quantum field theory, but some physicists see this as sweeping the problem under the rug rather than truly solving it. The continuum hypothesis asks about different sizes of infinity. The set of all integers is infinite. The set of all real numbers is also infinite. But the set of real numbers is a larger infinity. Cantor proved this by showing you can never make a complete list of all real numbers. There are always more. Are there infinities between the infinity of integers and the infinity of real numbers? The continuum hypothesis says no, but Gödel and Paul Cohen proved that the continuum hypothesis is independent of the standard axioms of mathematics. You cannot prove it true or false from the usual rules. You have to choose whether to accept it or reject it. This means mathematics has freedom in it. Certain questions do not have definite answers within the system. You can build consistent mathematical universes where the continuum hypothesis is true and others where it is false. Both are valid. Which one describes reality? We do not know if the question even makes sense. Prime numbers remain mysterious, despite being so fundamental. The twin prime conjecture says there are infinitely many pairs of primes that differ by 2, like 3 and 5, like 11 and 13, like 100000000000000000009. We have found enormous twin primes, but no one has proven they never stop appearing. Goldbach's conjecture says every even number greater than 2 can be written as the sum of two primes. 4 equals 2 plus 2. 6 equals 3 plus 3. 8 equals 3 plus 5. Computers have checked this for numbers up to absurdly large values, but no proof exists. These conjectures seem obviously true, yet we cannot prove them, and history is full of conjectures that seemed true until someone found a counterexample. Math is unforgiving. A single exception destroys a conjecture. Why does mathematics describe reality so well? The physicist Eugene Winger called it the unreasonable effectiveness of mathematics. We invent abstract systems of logic, symbols, and rules. Then we discover that these systems perfectly describe how the universe works. Einstein used Riemannian geometry, developed decades earlier, for purely abstract reasons to describe gravity. Quantum mechanics uses Hilbert spaces and linear operators. Particle physics uses group theory. Every successful physical theory is fundamentally mathematical. Is math discovered or invented? Do mathematical truths exist independently of human minds, waiting to be found? Or do we create mathematical structures and then notice they happen to fit reality? If math is invented, why does it work so well? If it is discovered, where do mathematical objects exist? Plato believed in a realm of perfect forms where mathematical truths reside eternally. Circles, numbers, equations all exist in this abstract space, and our minds access them through reason. This sounds mystical, but many mathematicians feel they are discovering truths rather than inventing them. When you prove a theorem, it feels like uncovering something that was always there. And this brings us to the deepest question of all. What is the nature of reality? Is the universe made of matter and energy, particles and fields, or is it made of information, of bits, of mathematical patterns? Is consciousness fundamental or emergent? Is the universe deterministic or probabilistic? The simulation hypothesis suggests we might be living in a computer simulation created by a more advanced civilization. If you can simulate conscious minds, and if simulations can contain their own simulations, then there could be vastly more simulated realities than base reality. Statistically, we are more likely to be in a simulation than in the original universe. How would you tell? Some argue that if the simulation has finite resolution, We might detect pixelation at small scales, glitches in the matrix, limits to computational power. The holographic principle in physics says the universe might indeed have a fundamental resolution, a maximum amount of information that can exist in a given volume of space. Is this a sign we are simulated or just a property of reality? Others say the question is meaningless. If the simulation is perfect, if it is consistent and obeys its own laws, then it is real for us. There is no way to step outside and see the original reality. The simulation is our reality. These questions might never have answers. Some mysteries might be unsolvable in principle. We are finite beings trying to understand an infinite cosmos. We are using brains that evolved to survive on the African savanna to comprehend quantum mechanics and cosmology and consciousness. It is remarkable we have gotten as far as we have, and perhaps that is the real wonder. Not that mysteries exist, but that we can even recognize them, that we can formulate questions about dark matter and time and consciousness and origins, that we have built telescopes to see billions of light years into space and microscopes to see individual atoms, that we have unlocked the genetic code and mapped the human brain and sent spacecraft beyond the solar system. Every answer leads to new questions. Every discovery reveals deeper layers. The more we learn, the more we realize how much we do not know. The universe is not giving up its secrets easily, but maybe that is how it should be. Maybe the beauty is in the mystery, the wonder in not knowing, the joy in asking questions, even when answers seem impossible. Tonight, as you drift towards sleep, think about the vastness of what we do not understand, the dark matter surrounding you, the quantum strangeness underlying everything, the origin of your consciousness, the beginning of time, the nature of reality itself. These mysteries are not problems to be solved and forgotten. They are invitations to wonder, reminders that existence is stranger and more magnificent than we can imagine. We are children of the cosmos, asking where we came from. We are patterns of matter that have become aware of themselves. We are the universe trying to understand itself. And in the quiet darkness, under stars whose light began its journey before humans existed, we continue to wonder, continue to question, continue to seek. The mysteries remain, and that makes everything more beautiful. Sleep well and dream of infinite questions.